How's it going, everyone? It's 2024, and we are going to ask the age-old question that year by year has a different answer, and that question is, which programming language should I use for computational science? And the answer to that is both going to depend on the year in which you ask it, and how the communities are supporting the languages and the packages in it, as well as your context and your needs. So in this video, we're going to try and address all of those points. What are the recommendations for which needs in 2024? And so a question just before we get started that's interesting and I should answer is, why should you listen to me? Like, what's my background? Why do you care about my opinion? You should care about my opinion because this is basically what I do. I'm more or less a computational physicist. I did my undergraduate degree in applied mathematics. Where I was, that basically means sort of numerical science in a very general term. And I did my master's and PhD in a very computationally physics focused group where we were really interested in physics that you couldn't do by hand. And as you could do something by hand, that's when you know it's still, of course, very interesting, but at the end of the day, the group was very much focused on, doing numerical methods and asking questions that you couldn't do by hand. And so this involved, and for me still involves, a lot of work with supercomputers, data processing, using computer algebra systems, and so on. I am now in England, continuing this journey. And again, I do analytical work, of course. You always need to do analytical work, but my primary tool going forward forever will be high performance computing, plopping stuff up on a supercomputer, writing novel algorithms, and so on. So what we'll do is we'll go through a list of languages that I think are popular choices that you'll hear about in context of scientific computing. And at the end of the video, I'll let you know what my current sort of workflow looks like. So, like all things, before we get started, why don't we ask AI what the correct answer is? The best programming language for scientific computing depends on a few factors, so there's no single answer. Okay, that's fair. So Python and R. I wasn't going to talk about R. I think R deserves a shout out for things like data scientists. Maybe these things will be much more. Maybe R will be much more interesting for people in biology, maybe chemistry. It's not popular at all in physics, and I've never used it formally. So Python is very, very beginner friendly. I am going to talk about Python, and I do use it in my workflow. Let's see. So performance-oriented languages, C, C++, we're going to talk about those. Fortran, we're going to talk about it. And Julia, we're going to talk a little bit about it, especially once I start making my recommendations. I think Julia and Python are going to be at the top, despite my current workflow. Matlab we'll definitely talk about. I don't think Octave is worth talking about specifically because of sort of package support, kind of a dead community. I apologize if I offended anyone who uses Octave, but I don't actually think it's a viable alternative to Matlab. And if you want a viable alternative to Matlab, I think Julia is the correct one. Like, I don't think that, when you're talking about pure performance, if you're really at that scale where performance really, really, really matters to you, Julia should not be in a list with C, C++, Fortran. It should be down with like speeds. It's certainly much faster than Python. Much, much faster. But it's probably more comparable to something like Matlab. Now, something that has been missed here are computer algebra systems, which I think for more analytically inclined people, like that's really what that's a skill that you really want to learn. And we'll talk about Mathematica and Maple at the end. So when we're answering our question for which programming language you should learn today, I think that there's basically about 5 questions you should try to answer before committing to that language. And you need to come up with your own ranking of which of these questions is more important to you. So first, I think it's really It's a really it's a very important question to ask if there is a large community of developers working on relevant packages. There are a lot of new languages, like let's say Rust, let's say Zig, and these languages are very cool and very novel. They are not scientific computing languages in the sense that you need a large community of people working on relevant packages um, to make them viable to the average scientist. They're going to be the peak people in computational science who might be able to hold a conversation with a computer scientist or a software developer, right? Most scientists aren't that, 99%. Scientists should typically, not always, shy away from trying to develop sort of core algorithms like on their own. I once knew a scientist who tried to write their own singular value decomposition. And it's like, why? Why would you ever, ever want to do that? That is such a waste of time. When your job is asking questions about phase transitions in quantum magnets, writing a singular value decomposition is an incredible waste of your time when there is like 60 years of history, 40 years of history of people writing extremely robust algorithms, right? So, in my opinion, is there a large community of developers here, and is there going to be good package support here? That's a really important question to ask, especially for the tasks that you're going to need to do regularly. The second one is going to be, does this language have a high learning curve? For the vast majority of scientists, overcoming a high learning curve, while it's tempting, scientists like to learn, overcoming that learning curve usually isn't worth it, right? Like for the vast majority of people, learning something as easy as Python, that is more than sufficient, right? If all you're doing is loading in data and doing some linear fits, maybe R and Python is all you need. If you're going to do something a little bit more medium difficulty, maybe a couple hundred lines of code, again, unfortunately, maybe Python's all you need, right? Like it might not be worth it unless there's a direction in your research and a direction in your skill set that you want to go past, easy to learn, interpreted languages. And the next one is sort of related to that. There's like an efficiency question of like you want tools that are efficient for your job. So is the language efficient for developing programs to answer the questions you want to answer? And it's probably indisputable that you don't want to be doing data processing in assembly, right? So that's like super obvious. And to be honest with you, for the vast majority of data processing that I've ever done, Python is more than efficient. You might want to go a step further depending on your requirements, but at the end of the day, you want a tool that's efficient for the types of problems that you want to solve, right? Now, another question for a lot of people, and this is for maybe more of the novel algorithms, people that want to push past barriers, and that's, what is the performance of your language? Does it have really good, parallel computing support? And depending on your skill level, where does that support sort of come in? Like if I'm coding on C++, it's not trivial, but it's relatively easy to, do GPU or, parallel CPU computing, right? It's probably not going to be as straightforward in higher level languages. And in higher level languages, like in Python, the simplicity that you get is paid for in slowness. There's the memes of Python for loops. And another question that I think is really important that you should always keep in mind is, especially if you're new, is do people in your field program with this? Because if there's new algorithms that are coming out in your field, then odds are those algorithms are being written in the most common languages in your field, right? Like linear algebra packages, a lot of them have like a Fortran backend. Um, unless I'm mistaken, tensor network methods are relatively new in physics right now, and as far as I'm aware, I don't think they're written in Fortran. The ones that I'm aware of are Julia, C++. There's some in Python, and so at the end of the day, the thing that I want to stress, because I've seen people, take very inefficient turns with their time, is that at the end of the day, what you really, really want is to pick a tool for your job, right? There are side benefits, of course, of other things where as if you're a grad student, for example, picking certain tools might not be as relevant for industry in case you want to exit, and that's also something that you should keep in mind. Okay, so for the first few languages that I'm going to talk to you about today are compiled languages, and these are for people that really want to go fast, and they want to write probably novel algorithms that are very computationally complex, right? And so just to get you started, I think that coding in some type of environment with Linux support, I know was it Visual Code or Visual Studio now has Windows subsystem, Windows Linux subsystem support. I think the best compiler for this is GCC. So GCC is free. A lot of your clusters are going to have like Intel compilers and proprietary compilers, but GCC is something you can develop on your local machine, and it's going to be available on the cluster as well. GCC is extremely efficient, and it's going to support the three compiled languages I'm going to talk about today: Fortran, C++, and C. Compiled languages are languages where you're going to write your code, you're going to then compile the code. The compiled step is a step where they're going to turn your source code into machine code. It makes the code extremely efficient, right? Your code's going to go very, very fast. The price for this is that you have to do things like strong typing. There's not going to be as high level of abstractions out of the box, and you're going to have to worry about a lot more things like garbage collection, making sure that you take care of memory. Let's jump into Fortran first. Fortran, very old. I think the first time it was compiled was 1958. But it's also new in the sense that it's still getting stable releases. As of, I guess, 3 months ago was the most recent stable release. It's very simple, bare bones to learn. There's a couple of data types. The syntax is, a little clunky. So here we are, for example, what we're doing here is we're saying this is an integer amount. We're saying there's a real number. Its name is pi, and so on, right? A weird thing about Fortran that I don't really like is that, for example, setting a value to a variable that you declare is, I guess it's not a normal initialization. I don't use Fortran, and I'll tell you why soon. But in principle, it's just bare bones mathematics. It's very functional. So, for example, a matrix multiplication looks like this, right? So you input matrix A and B, and out gets matrix result. Okay, so I think that my criticisms of C are going to be the same. So I think the simplicity of the language is, of course, what makes it extremely fast, being compiled, so on. But I actually think that abstractions like this, or I think that it not having object-oriented computing, hot take, is a huge downside. And not because I think scientists should be doing object-oriented computing, but I think object-oriented computing gives library and package developers the ability to abstract things to make code easier to use, right? So, for example, if I wanted to do an operation like adding to matrices, this performs sort of as I expect it. in Fortran, right? But then you need to always remember that multiplying this is these guys aren't actually matrices. A and B are arrays, and so this multiplies corresponding elements in array A and B. It does not do matrix multiplication. Um, and so this bare bones approach makes, in my opinion, code less readable. I mean, maybe that's debatable because maybe you prefer this because it's very explicit what this does rather than it being an ambiguous star. But I think that if I'm working under the impression that A and B are matrices, this behavior should be different. Maybe all I'm actually arguing for is that I think that a programming language for scientific computing should have data structures for arrays and matrices. Maybe that's what I'm arguing for. So Fortran is extremely fast, and if you're doing a lot of linear algebra, all of the old packages for linear algebra are coded in Fortran. So where is it? So, for example, LAPACK and like the LAPACK C interface, a lot of these things are going to work very similar. All of these things have a Fortran backend. Fortran's extremely fast. A lot of the old algorithms to do linear algebra are written in Fortran backends. So, as far as I'm aware, this is how Julia works. Like you can call LAPACK or you use LAPACK when you're doing Julia linear algebra. So I guess the question is should you actually use Fortran, right? And I think the answer is yes, if and only if people in your field use Fortran, and that's where all the software is being built. I think this is a terrible first language for people, and I think this is probably extremely inefficient to code modern algorithms if you're at sort of like a higher end of development. Data processing, uh, there's no plotting that you're going to want to do here. This is not a good first language, and I think even as a second language or like a high performance computing language, I think unfortunately, I know in my previous video someone commented, Fortran's the way to go. All these languages are compiled. All the compiled languages are going to be very fast, and so I just can't see why someone would do this when there's so little support compared to other modern languages. The next is C. I don't have a lot of good things to say about C. At the end of the day, I think that the way that it's taught online and the way that you're going to see a lot of resources being shown to you, things like pointers and memory management are going to take a front and center because this is a really big strength of the language. As someone who's taught C to second year scientific computing students, I don't think that this is a good language to expose people to for their first language, even their second language. And I'll get to why. Sort of a biased take coming up, I guess. But at the end of the day, I think functional programming languages are extremely limited for scientific computing purposes. I think they make things harder to write quickly. And I do agree that once you get sort of into that paradigm and you're very good at it, I do not doubt that there are extremely good numerical scientists working in C and Fortran because there absolutely are, right? I knew at the university I did my PhD at, there was an astrophysics group that did a lot of C, and I think this is basically why the second year scientific computing course was in C. But like unfortunately, like C is another language for scientific computing that I would say I would learn this if it's the common thing and this is where all the packages are. Let's get biased here. The next language that's compiled that we'll talk about is C++. The thing that you'll see about C++, which I think is kind of funny, is in the software developing circles. I watch a lot of YouTubers that do software development stuff, and what they'll say is that people don't actually like C++. They write C++ like it's C. And I think that's basically fair, and I would basically recommend that you do the same as a scientific computing person. That being said, I think that, when you're only using 10% of the language, you're ignoring all of the more complicated stuff. That's perfectly fine. However, C++ is an object-oriented language. And what that means is that just inserting one or two custom data types, whether by you or a package manager or someone with a library, that can significantly reduce the complexity of the code that you have to write. And I think a really good example of this is the Eigen C++ library. Okay, so Eigen is a linear algebra library. It's very high performant, and it's also extremely easy to write. I think one thing that I didn't mention is that Fortran and C. I don't know as much about Fortran, but C definitely installing libraries and dependencies is a nightmare. It's not like Python or Julia. It is a nightmare to get things working. Um, Eigen works as a header only library. You don't need to compile anything. You download a bunch of files and it just works. Now, the really interesting thing about Eigen is that it basically works like, as I was saying, there should be an array data type and there should be a matrix data type. It gives you don't need to do this ugly Eigen : if you put using namespace Eigen, it basically makes it so that you can easily initialize matrices of any size, and you can just use them mathematically like matrices. So this is a class. This is a data type, a data structure that they've made for us. And there's a lot of things sort of going on here, right? So for example, you can do matrix vector multiplication literally like this, or even a times equals if you really want to. And this really simplifies the complexity of the type of programs that you're going to write. And so, for example, you can do a trace, you can do an adjoint, you can do a transpose. All of these things are extremely easy to do just by including one library. Bare bones C++ probably wouldn't recommend it on its own, but I think that the sort of extra features that C++ comes with basically means that library creators can create spaces for people that make very domain-specific tasks easy. If you're going to learn a compiled language, I think C++ is the compiled language to learn today for now. Like, I don't think, for example, I think for example, if you're watching this, you might be thinking, why not Rust? And the answer is that I'm a scientist and not a software developer, and so you actually need mature packages and ecosystems that you want to use. Like I want to get to work. I want to do science. Like I don't want to make new tools. The things that we're worried about are potentially different. If you think Rust is a good alternative. Okay, so the next one is Julia, and this is one that I absolutely would recommend as your starter language. Julia is something that I haven't personally used, but everybody that I know that uses it swears by it. It was originally introduced to me when I was an undergraduate student as sort of like a free alternative to Matlab. My understanding is that the linear algebra is very fast in Julia. It does something called just-in-time compiling, so it's not as fast as a fully compiled languages. There are certain optimizations that are missing in Julia, but for all intents and purposes, like, this is not the downgrade that Python is. Creating a 3x3 matrix, getting trace, determinant, all of these things just come, very, very cleanly in Julia. And from my understanding, the package manager is very good, and the community is very good. So Lepac and Blast, like, these are Fortran, but that's fine. Fortran powering your backend, why not? Like, you can't do better than that. The one thing that I've heard about Julia is that it doesn't have very good plotting. So Matplotlib that we'll talk about in Python is really, really hard to beat. But I think Julia is actually like a very good choice to get into as your first step in scientific computing. Like look how clean this is, right? I guess this is kind of weird syntax, the dot there, but I guess there's not a lot of features or there's not a lot of options for plots. Like I don't really know what the problem is, but I mean, you can always generate data in Julia and port it over to port it over to whatever plotting software that you like. Like these don't look so bad to me, to be honest. Like these aren't more complex than the ones that I make usually. So from the perspective of community, I would say Julia is really good. There's lots of scientists that are very enthusiastic about Julia. There's lots of good software developers who are working on it. From the perspective of learning curve, Julia is the easiest to learn of all the languages we've discussed so far. So Fortran, not so bad. C, in my opinion, not so great. C++, sort of a mountain, but you can stay at the bottom of it if you want to. Julia is by far the easiest to learn, and it's performant. I would say that it's becoming also a lot easier to solve the types of problems that you want to solve. So, for example, um, a big thing in physics right now is tensor network methods, and unfortunately, probably the best tensor network library actually switched from C++ to Julia. And from my understanding, one of the reasons was A, it's not that big of a downgrade in terms of performance. I mean, it is a downgrade, but not a crazy downgrade. And B, it's easier for users to get started, right? Like in C++, they had a whole CMake system. It was, from like a new person's perspective, it was probably extremely complicated to get iTensor just to work, let alone like actually using some of their things. A lot of their documentation was also really opaque in the sense that they used a lot of the auto symbol in C++, so it was like kind of difficult to understand what was happening. Yeah, I think that Julia is just simply, and it's also a language that you can get really into optimization for. So it's sort of you can start low and not really care about performance, but as you start caring about performance, there's lots of ways to make Julia faster. So in my opinion, this is a great starter. So the next one up is Python. Now, I wouldn't recommend just plain Python, of course. No one in their right mind would do that, especially for scientific computing. I think there's two really good options for scientific computing in Python, and that's going directly into the Spider editor. This is what I do. You can see down here. Or to use Jupyter Hub, which is much more interactive. I personally like Spider because it's developed specifically for scientific computing, not sort of data visualization and things like that, which I think Jupyter excels at a bit more. And of course, I love my Variable Explorer. Variable Explorer is a very cool feature. I'm impressed very easily, apparently. But out of the box, so the way to get good at Python is to do as little native Python as possible. So being able to do advanced initializations of, say, NumPy arrays. NumPy is numerical Python, I think is what it stands for. And it's a backend or it's a library that's written in C. Python is a very good sort of pipeline from Fortran, C, C++ into Python, so you can write libraries. And basically your goal at getting better at this programming language will basically boil down to not doing the programming language. You're going to be working in, sort of like NumPy arrays and things like this, manipulating those efficiently. But from the perspective of data processing, packages and support for basically every possible problem that you want to solve, someone probably made a package for it. Whether or not that package is good is another thing. Most of the time, there's multiple options, and there's a best one out of the bunch. So I would absolutely recommend this as sort of as a beginner, an all-encompassing sort of beginner language. It's easy to learn. There's a large community with it. It's not performant, but from a developer efficiency standpoint, answering the questions you want to answer, there's nothing more efficient than Python. Maybe Julia is a competitor here. And it's extremely common in science. Most people work with Python, for better or for worse, right? As someone who values speed, it is unfortunate that maybe the scientific computing sort of institutional knowledge at a lot of universities has gone down significantly. But I would recommend Python as a starter. Now, some honorable mentions are Mathematica and Maple and Matlab. Matlab is Matrix Laboratory. You're not going to get faster linear algebra than Matlab. It works a lot like Julia. It's a sort of a like Python is all encompassing, but Matlab is made for scientific computing, engineering, lots of packages and supports for Matlab, and a lot of universities teach it. So from the perspective of as long as you have as long as someone else is paying for your Matlab license, it's not a bad skill to pick up. But of course, I don't really know how common it is in industry. But I do agree that as a beginner language and being able to do a project start to finish, in terms of idea to publication, MATLAB is a good choice. C++ is not a good choice for that, right? C++ sort of, in my opinion, that workflow ends at data generation, and then you do data processing somewhere else. MATLAB is a good choice in my opinion, unfortunately, but I think there are a lot of strong opinions out there against it. But in terms of speed, readability, community, getting projects off the ground, like unfortunately, there's nothing really wrong with it in terms of scientific computing. Now, something that's kind of special that I don't know how common it is in other fields to work with this is sort of symbolic computing platforms. So Mathematica and Maple are two options like that. I don't think you can go wrong with either. I think Maple's like UI is a little bit uglier than Mathematica. Mathematica is really nice. I'm going to show you something super silly and easy, but these systems can help you do math like a human, right? So these symbols are treated symbolically. This is a super simple and super silly example to give you guys, but I guess hold on. I'll give you something like minorly better. So a minorly better example would be something like this, constructing so we have qubit operators, the poly x, poly y, poly z, matrices, and then what we're going to do is we're going to make xx, yy, zz, and we're going to make a unitary matrix out of it. So to do that, I'm going to take a matrix exponential, and then I'm going to tell Mathematica to simplify the expression as much as possible. And I'm also going to put it in matrix form because it has weird syntax. And basically, it treats JX, JY, JZ as symbolic parameters. I could input them later, but in principle, it simplified the mathematics for me here. And so a lot of really good analytical people are very, very good with one computer algebra system, symbolic computing system, whatever you want to call it, Mathematica, Maple, whatever. This is a skill that does not translate over into industry, of course, as far as I'm aware. I mean, maybe there's a niche for it. But these systems are extremely powerful. They also have things like you can do numerical precision to like arbitrary order, for example. You can have arbitrarily large integers. In other systems, you're going to have like 64-bit integers or 64-bit doubles or real numbers, right? The default is the same in Mathematica, but in principle, you can ask them to increase the precision. Like everything is symbolic, everything is negotiable. As long as you have the RAM for it, it's fine. And so if you are in the position right now where you are a numerical person, mastering Mathematica or Maple is certainly a good idea, or some type of symbolic algebra support. Okay, so we've sort of talked about all of these options. I basically recommended, if you want to go high performance, I recommend C++ as your starting point. If you want something that's sort of like in the middle, I would say Julia. And if you want sort of like the easiest possible path as a starting point, I would recommend Python. And what I do in my workflow is, one, when I do analytics or when I need to do something like this, I use Mathematica for now. I've used Maple in the past. I don't think there's anything wrong with Maple, except for some of the syntax is wonky. But there's gripes with with all languages, right? Um, and for high performance computing, I use C++. C++ because a lot of what I do is tensor or linear algebra based, basically. And with Eigen, that's more than I could ever need. And then it has very good, parallel computing sort of support. So I use OpenMP and MPI when necessary. I haven't learned CUDA yet, but that's sort of on the list. That's where I generate all my data. And then the next one is Python. I do all my data processing and plotting in Python. And I know people that do all their data generation and their plotting in Python. And it's really nice because NumPy is a very, very good library. There's extra libraries like pandas, and there's lots of things like Numba that will try and make your code a little bit faster and so on. The Python community is extremely large and has a lot of support. You can't go wrong starting there, but I think that if you do get to the point where you're frustrated with code execution speed, um, moving on to Julia is a good next step. Um, but C++ is sort of where I'd recommend if you went the compiled route. For now, maybe that'll change in the future.